I'd like to welcome you to today's webinar, Efficient Processing for Deep Learning, Challenges and Opportunities, organized by the Embedded Vision Alliance. My name is Brian Dipert. I'm the Editor-in-Chief of the Alliance, and I'll be your moderator for today's event. Your presenter is Dr. Vivian See, Associate Professor in the Electrical Engineering and Computer Science Department at MIT. At this time, I'd like to turn the microphone over to Professor See to begin the presentation. Professor See?
Thank you, Brian. All right, so today we're going to talk about efficient processing for deep learning. In particular, we're going to look at both the challenges it presents and then understand some potential opportunities that we can have at various levels of the design. Just very briefly, in terms of motivating why we care about deep learning in particular for embedded vision, is that we know that video is the biggest of the big data. It dominates communication, so over 70% of today's traffic is to communicate video. The amount of video that's being generated is huge, so if we just look at consumer electronics, we're looking at 300 hours of video that's uploaded to YouTube every day, or actually every minute, and then over 500 million hours of video surveillance that's collected every day. So obviously, the amount of video is more than what a human can analyze. In many of the cases, we would like to do the process locally on an embedded device. This could be for privacy reasons, because we don't want to share the data. It could be latency reasons. So for example, in a drone for navigation, you can't tolerate the communication delay, or sometimes you just don't have connection to the cloud at all. But unfortunately, the amount of processing that you have on these embedded devices is limited due to the energy capacity of the battery itself. So the default option that we have today is you do the compression on the device and you send the compressed video to the cloud, and then the data is processed in the cloud itself. The challenge there, of course, is even in the data center itself, there are limits to the power consumption due to heat dissipation. So regardless of where you're doing the processing, one of the key goals, and this hopefully aligns with a lot of the interests of the listeners, is that we need energy-efficient pixel processing. The other thing that's become quite interesting is obviously deep learning. The type of processing we typically want to do these days is deep learning, because it gives us very high accuracy in terms of our ability to extract information out of this visual data. So as we've seen in the past from the ImageNet competition, we can see that ever since from 2012, when we switched to deep learning approaches, the error has been significantly reduced to the point at which we can exceed human level accuracy. So while deep learning is great, it provides very high accuracy, the main challenge here is that it requires significantly more computation than previous approaches. So really the objective of today's talk is showing how we can kind of have our cake and eat it too. So how can we achieve high accuracy, but also meet the energy requirements on these, either on these embedded devices or even potentially in the data centers. In particular, when we're discussing visual data, the type of deep learning that we care about is deep convolutional neural nets. So briefly first go over kind of a very brief tutorial, but what are the key components of neural nets, and also to align our terminology together, since this area has been explored in various different fields. So we know that in modern deep convolutional neural nets, we have several convolutional layers which extract from the beginning of the network the low-level features, and as you go deeper into the network, higher-level features. And the number of layers or convolutional layers that you have in modern CNNs are quite high. So it can go up to, in some cases, 1,000 different conv layers. This is typically followed by 1 to 3 layers of fully connected layers. Now, the key message that I want to highlight here is, in terms of the convolutional layers, the convolution computation itself accounts for over 90% of the overall computation, and it dominates both runtime and energy consumption. So what you'll see in today's talk is mainly focusing on how we can address the issue of these very expensive convolutions. To give you a better idea in terms of what is involved in these convolutions, we'll briefly go over the key steps in the convolution, but particularly why convolutions for CNNs are more complex than traditional image processing. So if we look at the data that we have, so let's say we have an input image that's of 2D size, and we convolve it with a filter that's also 2D. What we're essentially doing is that we're doing an element-wise multiplication of the weights of the filter to either the pixels or the activations of the input image or feature map in itself. And then once we do an element-wise multiplication, we add the values up, these partial sums up, and this generates one output pixel. And then we can drag the filter across the input image through some form of a sliding window process to perform convolution, and we generate other pixels. So this whole process we've just described is very common in image processing, and that's been done for decades. So the real question that we have is, why is it more complicated for CNNs? Well, that's because in CNNs, we exploit a higher dimensionality. So for instance, within a CNN, we actually, rather than just the height and width dimensions, we also have a channel dimension, or a third dimension. So for an input image, you can think of this third dimension as the color component, so the red, green, and blue components. And so the filter itself becomes a 3D filter. Just to give you a feel in terms of how large the channels could be, if we think of AlexNet, which was the winning architecture for the image back in 2012, which really started this whole trend, the number of channels can go from 3 to 192, right? So that's quite large. We're already talking about a significant increase in the amount of data that we have to process. Furthermore, we don't just apply one filter to a given image or feature map. We actually can apply multiple filters, right? And each of these filters, when we convolve it within the input feature map or image, we actually get one output channel. So if we have M filters in total, we generate an output that has M channels. And again, to just give you a sense of the size or order of magnitude of the filters themselves, when we talk about AlexNet, we're talking about 96 to 384 filters, right? So that's a huge amount of data and a huge amount of processing. And then finally, of course, as we know, you typically have to process more than one image at a given time. And this is typically referred to as a batch of images. And these sizes can range between 1 to 256. So you might be processing 256 images at a given time. And as you can see, the number of input image would equal to the number of output images. So the one thing I really want to highlight and note about these filters themselves is that they're large in size and they vary in shape. So if we look at AlexNet as an example, we can see that for each layer, the filter size will change. It goes from 11 by 11 to 5 by 5, and then 3 by 3 for the rest of them. Furthermore, the number of filters will change, and the number of channels will also change, as well as the stride. So even though, as we have seen more recently, that there are some neural networks out there that use the same filter size, they still vary in terms of number of filters and number of channels. And so the one message I really want to get across here is that we need to have hardware or solutions that are flexible enough to support a wide range of filter sizes, number of filters, and filter channels. The second point that I want to get across here is that the size of the filters themselves are very large, right? So if we look at, for example, layer 1, we're talking about 34,000 weight parameters only. This doesn't include the input data. And when we go all the way to layer 3, we're talking about over 800,000 weight parameters. So that's a lot of storage and data that we have to manipulate just for the neural net. This is not even including the actual image data itself. Furthermore, we need to do a lot of computations for each of these layers, right? So we're talking about at layer 1, hundreds of millions of multiplications that accumulate, and it's going up to around 200 for layer 2, and similarly very close for layer 3. And again, this, if you're not familiar with convolutional neural nets, this is to process an image that's of size around 224 by 224. So you could imagine as the resolution increases, the potential of requirements in terms of compute will also go up significantly. So we've seen many popular CNN architectures over the past couple of years. In particular, the ones that typically stand out are the ones that have done pretty well in the ImageNet competition. So we talked a lot about AlexNet. Also, there's Overfeed, VGG, and GoogleNet, and ResNet, and so on. And ResNet was the first one that beat the human-level accuracy. I should mention that a lot of the origins of convolutional neural networks came from the work from Jan LeCun back in 1998 when he did LeNet. So the idea of CNNs has been around for decades. The main difference now is that the networks are larger, meaning they have more convolutional layers. Each layer has more filters and have more channels. And now we have more data that we can use to actually train these networks. And then we also have a lot more compute power that enables us to do that. When we're looking across all of these different CNN architectures, as we've shown here, a couple of things should stand out to us in terms of trying to identify trends in this area. So the first thing is that we can see that the number of convolutional layers has increased, right? So from the case when we're talking about LINET, which is doing digit classification, that's gone from 2 layers, and AlexNet was 5 layers, all the way up to 50 layers in ResNet. And ResNet has some work that shows also in 1,000 layers, over 1,000 layers. The other trend, and as you can see, as I mentioned before, the number of the filter sizes will vary, the number of channels, the number of filters, and so on. The other trend that we've noticed is that the fully connected layers have actually reduced in terms of the number of layers. So in LINET, we used 2 fully connected layers. In AlexNet, we had 3. But the issue that all the designers kind of noticed was that if you look at AlexNet, majority of the weights were located in the fully connected layers, right? So we had around 60 million, almost 60 million, 58 million weights were in the fully connected layer out of the total of 61 million weights. So since then, starting with GoogleNet, the number of fully connected layers has reduced from 3 to 1 to substantially reduce the number of weights there. And so as you can see, the overall trend is convolutional layers get deeper and fully connected layers reduce. And so overall, now when we look at, for example, ResNet, the majority of the weights and the computations are actually happening in the convolutional layers as opposed to the fully connected layer. So as we move forward, one of the things that we should consider is that convolutional layers, particularly for CNNs, are becoming increasingly important, and that's something that we should really focus on developing methods for efficient processing. The other thing I want to highlight before we get deeper into this is that obviously there's 2 modes when we're talking about deep learning. One is the training mode, where you're taking these very large data sets, and from these very large data sets, you're trying to determine the weights of your neural network itself, so the weights of those filters that we were talking about. That's typically occurring on the cloud. And then what happens is when you actually want to use the neural network that you've trained on these large data sets, you perform a task that we call inference, and this typically works on these embedded devices. So you would download the weights, the trained network, the trained weights from the cloud onto these devices, and then use these weights to perform the convolution. So in today's webinar, we're going to primarily focus on the inference task itself, because that's typically what occurs on these embedded devices. So what are the challenges that we actually face within this space? So I really want to summarize kind of all the different metrics that we actually do have to hit in order to have a very useful and feasible embedded solution using deep learning. So obviously the first thing that you should consider, or the first important metric that you should consider when evaluating or designing these neural networks is accuracy. If you take a step back, why are we excited about deep learning? Again, if you recall, it's primarily due to accuracy. So when evaluating a deep learning solution, we want to know what the accuracy, but in particular, you want to ask on what particular data set and doing what particular task. So for example, I've shown here on the upper right-hand corner, we have the MNIST and the ImageNet data set. So MNIST, again, is a very old data set that was used, for example, with the LINET convolutional neural net, is to do handwritten digit classification. And now you could imagine that a neural net that's designed for MNIST is going to be much simpler than a neural net that's going to be designed for ImageNet. So when we're trying to compare embedded solutions, we should definitely take this into consideration, right? So ideally, what you'd like to do when you're trying to compare different platforms, that would want to compare these platforms or these deep learning systems for the same DNN model, doing the same task on the same data set for a fair accuracy comparison. The second metric that we care about is programmability. So we know that deep learning and convolutional neural nets are used for a wide range of computer vision applications, and in some cases it's also been shown to be useful in other applications like speech recognition. So you want the networks to be very flexible. We saw that already within the network itself, the shapes of the filters can vary. And obviously we want to be able to load different weights onto the system. So the reason I'm mentioning this is one of the trade-offs of making things more efficient is to make things less flexible and less programmable. So there are cases where people think, oh, can we just hard code the weights, hard code the filters, right? And we can make it more efficient that way. However, here you have to always keep this programmability in mind, because even within the network itself, you need this type of flexibility. The next thing gets very closer to what we're going to focus on today is energy and power consumption. right? So obviously on these embedded devices, we have limited battery life, as we mentioned, so we want them to be energy efficient. And in the data center, you don't want to dissipate too much heat, so you need to be power efficient, so reduce the power consumption. One thing I want to highlight is that often when we're looking at these systems, we're looking at not just the hardware, the chip itself, but we should also consider the off-chip memory. So as I mentioned, in computer vision, particularly deep learning and dealing with video data, there's a lot of data movement, and we will soon see that data movement actually consumes much more energy than the computation itself. So although it's important to look at the energy per operation, you also want to make sure that you're factoring all data movement, including off-chip DRAM bandwidth. Next, we also obviously care about throughput and latency. So you want, for instance, for your hardware or system to be running at a reasonable frame rate. If it's in the cloud, you want to be able to potentially parse through a lot of data for high throughput analytics. Latency is also important. So depending on if you need to have a certain reaction time, for example, for speech recognition or even for navigation, you want to make sure that you're able to deliver the results very quickly. So I do want to distinguish the difference between throughput and latency. Throughput means that I can complete, an average time, let's say, of 30 frames per second. But often the case is, in order to achieve high throughput, what you need to do is bundle or batch the number of images together to hit that throughput. What latency tells you is that it tells you how many frames you can actually bundle together. So typically, for a very low latency application, the number of images, the batch size that you could have would be equal to 1. And then finally, when we're assessing these type of systems, cost is also very important, right? So as we know, one of the primary costs is the cost of the chip fabrication itself, for example. For those of you who are just buying processors, you can imagine chips that are larger with more memory and more cores will cost more, right? So that should also be kind of taken into account when you're assessing a deep learning system for its efficiency. Obviously, if we have a higher cost system, we could potentially be more efficient and achieve higher throughput, right? But what you want to effectively do is to have an efficient trade-off between all these different metrics, right? So you don't necessarily want to have a very expensive chip for higher throughput. Ideally, what you would want to have is a low-cost solution that still delivers high throughput and high energy efficiency. Okay, so what are the things that we can actually do to address these metrics and simultaneously satisfy all of them and achieve efficient trade-offs? So I'm going to cover kind of 3 key areas where we can do this. Or 3 different opportunities where we can do this. So one is looking at how we can actually map the algorithms onto existing hardware itself. That's the first one that we're going to cover. Just as a preview, the other 2 that we're going to talk about is how could you also develop more custom hardware to efficiently support these networks. And the third, which is also very exciting, is how can you now, if you can do custom hardware and change the algorithms, how can you jointly design the algorithms and hardware potentially together to make them more efficient? So let's first start with opportunities in the architecture itself, which means taking the neural network and mapping it onto existing hardware. So as we know, kind of the devices of choice for general purpose compute that's being used for deep learning are GPUs and CPUs in some of these cases. So we have, for example, Nice Landing from Intel, and they're releasing the next version, which is going to be more optimized for deep learning, and we know that people have been training and using GPUs from NVIDIA for deep learning over the past few years. If we're thinking about the compute on these particular devices, the main thing that we do is that we reformat, and I'll explain how that happens, is basically take these convolutional neural nets and map them to a matrix multiplication, and then we exploit these matrix multiplication libraries that are already available in the ecosystem of the CPUs and the GPUs, right? So we know for matrix multiplication, general purpose matrix multiplication, we know that CPUs have various different libraries like cuBLAS, Intel MKL, and so on, and GPUs, you can have cuBLAS and cuDNN and so on. The first thing, of course, here that you have to do is you need to be able to tile or basically select a size of the data that you want to process at a given time so it fits well into the storage hierarchy of these devices. So that would be the first exercise that you want to do, but beyond that, I'm going to talk a little bit about some of the other additional optimizations that you can achieve. So the first thing is just to briefly explain how we can relate the convolutional aspect that we just discussed before to an actual matrix multiplication. right? So if we see this example here, let's say we have a 2x2 filter, and we want to convolve it with this input feature map that's 3x3, and we generate an output feature map that's 2x2. What you could do is you could expand the filter from this 2D into a 1D, and then what you would do is you would, for the input feature map, you would do a Toeplitz matrix expansion. So you can see as shown here, and the main drawback here, or the main thing you would notice, is that there's a lot of repetition in data, right, in terms of the organization. So matrix expands, there's some repetition, but this basically enables you to basically do an easy matrix vector multiplication with the filter and the input feature map to generate the output feature maps. So really, whenever, and you can imagine that as you stack more filters here, you would generate more output feature maps, and this would become from a matrix vector multiplication to a matrix multiplication. So the real thing that you want to do on these particular platforms, the CPU, GPUs, is you want to reduce the number of operations so you can increase the throughput. Specifically, the type of operations that you aim to reduce are the multiplications, right? So what you want to do is do some computational transform so that bitwise you achieve the same results, but you've reduced the number of multiplies. And really the focus is on compute and primarily increasing the throughput. So an analogy in terms of how to understand what people are doing in this space is looking at Gauss's multiplication algorithm. We're going to use this as an analogy. So let's say you're multiplying two imaginary values with a real and imaginary component. You would generate an output value that also has a real and imaginary component. To complete this computation, you would take 4 multiplications and 3 additions. Alternatively, what you could do is you could pre-compute these intermediate variables. So K1 would be basically A plus B, and then you multiply it by C. K2 is going to be D minus C, and you multiply it by A, and then K3 is going to be B times C plus D. And then you basically, from K1, K2, K3, you can compute the real and the imaginary component. And why would you want to do that? Well, the benefit is that you're able to reduce the number of multiplications from 4 to 3. The cost is that you've increased the number of additions. But generally speaking, we're typically focused on reducing the number of multiplications, right? And so by reducing the multiplications, you can effectively increase the throughput of your system, right? So there have been various explorations in terms of how to actually do this. I don't have time to go into the details of each of these, but I just want to highlight some of the work that have investigated how to do these type of transformations to reduce the number of multiplications. So the first most popular one that's widely used is the Winograd transform. One of the key advantages of it is that it can provide significant speed up. So particularly, it's typically done for the 3x3 filter, and you get about a 2.25x speed up. The challenge here is that you need some form of specialized processing depending on the filter size. So the type of transform that you would do would change depending on the size of the filter. So primarily in practice, people use this for the 3x3 filter. Another very popular and widely known transform that's used here, but also widely in image processing, is the fast Fourier transform. And so when you compare direct convolution, which is basically would be O to the power of 4, when you use fast Fourier transform, you reduce that to n squared log n. The drawback of the Fourier transform is that primarily it does better the larger the filter you have, and as you'll notice later, the size of the filters, the trend is to reduce the size of the filters. And also there might be some increase in storage requirements, because typically the size of the transform is usually dictated by the size of the largest input, and as your filters are shrinking, if your largest input is your feature map, your transform would be dictated by the size of the input feature map. Another approach that people have investigated is the Strazen approach, but that's not as widely used as the Winograd and the fast Fourier transform. So if you look at the speed ups, particularly on CUDNN over the past couple of years, what they claim is that you're getting a 60x faster training in the past 3 years. Part of it is obviously new hardware, so you can see it goes from K40 down to up to P100, but the other is the CUDNN itself, and within that library itself, it's actually leveraging these transformations, both Winograd and FFT, depending on the size of the filter itself. Okay, so these are the types of things that you can do in terms of if I have CPU or GPU, if I want to change kind of how it would map the neural network onto this hardware. These are the different things I can do. Can I transform the neural network itself, get bit accurate results, but do it in such a way that I minimize the number of multiplications that I actually have to The next thing that we're going to briefly look at is how can you, or what are the things that you want to think about when designing specialized hardware, what we refer to as accelerators, for deep neural nets. So what are the properties that we can actually leverage in neural nets that are friendly to hardware? So obviously the first one is that it exhibits very high parallelism. All these neural networks, all they actually are just multiplies and accumulates. And so high throughput is really possible. But what is the actual challenge that we're facing? Well, the actual challenge is memory access. That's the key bottleneck. So if you think about each multiply and accumulate, we actually require 3 reads. So the filter weight, the image pixel or feature map activation, and then the partial sum. And you would generate 1 memory write, so the updated partial sum. So for each computation, you have 4 memory accesses, right? So that in itself already gives you a hint in terms of the ratio of the work. Secondly, in terms of energy, if we think about energy itself, accessing memory is actually much more energy costly than doing a computation. So in the very worst case, you would access this data from an off-chip DRAM, and we're talking about orders of magnitude. So in this case, we're looking at 200x more energy to access one piece of data from the DRAM than it is to do a multiply and accumulate on chip. So in the very worst case, if we looked at this, to do this, 700 million max you might want to do for AlexNet, you'd need 3 billion DRAM accesses. However, not all is lost here. There are still some opportunities to help address this in the neural network itself. So one thing that we can do is leverage what we call data reuse. So the question is, if I read something once of the input data, can I use it multiple times for many different operations, right? And when I read it once, can I bring it on chip to exploit what we call low-cost memory on chip? So there's various reuse opportunities that we can see in the neural network. So I'll basically first walk through the 3 different types. So the first, what we call convolutional reuse. So if you think about the fact that we're dragging a filter, convolving a filter with the image, for each convolutional operation, we're basically using the same sets of pixels and weights, just in slightly different combinations. So you can imagine if you read these pixels and weights on chip, you can use them multiple times for different operations. The next thing is what we call image or feature map reuse, and the idea here is that multiple filters are being applied to the same input image or feature map, and so each pixel or activation in the input feature map is going to be used multiple times across filters. And then finally, we also have what we call filter reuse. So now, as you recall, for some applications, we want to process multiple images at the same time, or a batch of images. And here, you can use the same filter across all of these images. And so what we say here is filter reuse, because the weights of the filters are you read the weights once onto the chip, and then use it multiple times across all the different images. Okay, so in terms of the types of architectures that we can use to investigate or exploit this reuse, there's 2 different types of architectures. So one is the temporal architecture, and here this is using SIMD or SIMT, so this is very similar to the architecture that you would have in a CPU or GPU. The idea here is that you have multiple ALUs, they all share the same control, and they all share the same register file, right? So they're all working pretty much together, doing the same operations and sharing and pushing the memory straight to the register file. An alternative architecture that you can explore in terms of doing this is what we call a spatial architecture. And the spatial architecture has a number of advantages over the temporal architecture. So the first thing is that it's very efficient in terms of data reuse. So what we want to do is, rather than having one single register file that's used by all the memories, we want to break this register file up and basically allocate a small piece of memory for each of the ALUs to bring the memory closer to the compute. And when you do this, it tends to be much more energy efficient. The other is that you want to also spread the control across all of these ALUs so they can operate more independently. And this register file, when I'm talking about this register file, I mean a very small memory. So we're talking about 0.5 to 1 KB of memory itself, right? Because typically what we'll see is that the smaller the memory, the less energy it consumes. The other advantage of these spatial architectures is it allows for inter-PE communication. So you can actually share data amongst the PEs. So you can imagine, once you read one piece of data from that expensive memory hierarchy from the DRAM, you can store it locally in the register file, and then you can also move it to your neighbor and share it with your neighbor, which is much cheaper than getting that data again from off-chip. Again, I really want to emphasize, if you're going to take anything away from the energy aspect of this talk, is that data movement is very expensive. Okay, so just to give you an idea, let's say an ALEO multiply and accumulate is 1x. Reading from this local register file, which we're saying is around 0.5 to 1 KB, is also going to be around the same amount of energy. Reading from your neighbor is going to be twice the amount of energy, and then going off chip, or so going to the global buffer, which is much larger, is 6 times the energy, and then to the DRAM, it's much more expensive. So really the objective here is we want to maximize the amount of reuse that we can have at the lower levels of the hierarchy. How can we read as much as possible from the cheapest memories? But the challenge here is that the cheapest memories are very small relative to the DRAM, right? So if you want to think about it, that we have this very large neural network, how can we grab a small chunk of the neural network, bring it out onto chip, and do as much processing on it as possible before kicking out and grabbing another piece? So there have been different strategies that people have investigated over the past couple of years on how to do this. So I'll just briefly walk through the approaches that people have taken. So one is what we call weight stationary. The idea is that basically within the register files, we store the actual weights of the neural network. So the weights don't move. So you're always reading the weights from the cheapest memory, which is the register memory, register file memory. The trade-off, of course, is that the partial sums and the pixels will have to move through the array itself and come from the global buffer, which could be more expensive. The flip side that some other people have looked at is what they call output stationary. So the idea here is that I don't want to move these partial sums, basically the products of the multiplies, throughout the network itself. I want to keep them locally within the PE. So what they want to do is that each processing element basically computes one of the output values. That's why the output is actually stationary. The outputs don't move. So all the partial sums are read and written from that register file, which is the cheapest memory. Of course, the trade-off here is the pixels and the weights have to move through the system and from that expensive global buffer. Finally, one strategy that other people have looked at is looking at what they call no local reuse. The idea is that these small memories are very inefficient in terms of area. They might be energy efficient, but the amount of bits that I can store for a given amount of area is very low. So instead of having local memories, I'm going to aggregate all that area and just have one huge global buffer so I can store overall for the same size of the chip, I can store a lot more data. But of course, the trade-off is that everything else has to move a lot throughout the chip, but you're reducing the amount of DRAM accesses. Something that we've developed in our group is looking at more of the row stationary data flow. I'm not going to talk too much about it, but the idea is that within each processing element, you store both a row of pixels and a row of filters, and so you can have more reuse across these different, the pixels and the filters themselves, some convolutional reuse there, and then also you'll move the partial sums throughout the array itself. So if you're going to take another main message out of this, when we look at all the different types of data flows or how you're going to move the data through the network, what you can see is using a row stationary data flow is more efficient than the other approaches. The one main reason you can take away from this is that it optimizes not just the weight energy. So the weight stationary, as expected, the weight energy shown here in green is the lowest, but the partial sum and pixel energy goes up. Whereas the output stationary approach, the partial sum energy is the lowest, but the other forms of energy, weights and pixels, go up. In the row stationary approach, we really focus on not just optimizing the energy of one type of data, but actually looking at the overall net result of all the different types of data together. And as a result, you can drop the energy consumption from 1.4 to 2.5x. You might have all heard of this, Iris accelerator. Primarily, if you're going to take anything away, the Iris accelerator is basically a piece of hardware that we built to support this row stationary data flow, so really minimizing the amount of data movement that you have both on chip as well as going on and off chip, and it uses a spatial array of 14 by 12 processing elements. When you compare this Iris accelerator to an embedded GPU, so at the time this work was from 2016, so at the beginning of 2016, so what we were profiling then was the TK1, you can see that despite the fact that Iris is at an older process technology, it has about half the throughput of TK1, but has measured power that's about 20 times lower. So overall, you're getting about a 10x improvement in energy efficiency. So if there's any more interest in Iris, you can visit the Iris website. But the one thing I want to highlight is that despite having kind of specialized hardware for deep neural nets, which is the Iris chip, so we've plotted in this case the accuracy versus energy of this, so looking at AlexNet and VGG on the Iris chip. When you compare that energy versus let's say, video compression, which is present in all devices that have kind of some kind of sensor, or the energy that you would consume for, let's say, doing hog feature extraction, we're talking about an orders of magnitude gap in terms of energy. So over 100x higher energy for AlexNet, and almost, I would say, also 10,000x energy in terms of VGG16. Right. So despite the fact that we're increasing the accuracy, the energy cost is really substantial. And this is, of course, already for we're comparing two pieces of custom hardware in this particular example on the same process technology. So if we take a step back again, if we're trying to look at developing a system, we really should be asking ourselves, is this energy versus accuracy trade-off something that is, of interest, or is this something that is attractive to someone who might want to use the system? Is someone really willing to pay, for to have your battery run out 10 times or 10,000 times faster, if you just to have about a slight increase or an increase in accuracy? So the real question is, can we do something more than just developing custom hardware to make the energy and accuracy trade-off better? So obviously, one of the areas that people have really explored is looking at the idea of joint algorithm hardware design. And the idea here is that, can I make the algorithms themselves more low power friendly? So this is also an area that's had a lot of research over the past couple of years, and there's been various approaches in this particular space. Loosely, I would categorize them as the first category is reducing the size of the operands for storage and compute. So this is looking at things like going from floating point to fixed point, doing bit width reduction, and even doing some nonlinear quantization. Another area that people have been really looking at is just, rather than reducing the size of the operands, can we just reduce the number of operations of the storage and compute? So this is looking at things like exploiting activation statistics, network pruning, and compact network architecture. So I'll briefly kind of walk through some of examples of each of these different approaches that people have taken in terms of, again, how can I, rather than designing my neural network just to improve accuracy, how can I design it to be more low power, high throughput, more efficient? So we know, there was a big amount of debate back in around 2014, 15 in terms of, what accuracy, computation accuracy is enough in terms of the precision of the actual operands and the operations. And then in 2016, Google's TPU came out, as well as NVIDIA's Pascal, and both had 8-bit integer support. So at least for the inference task, it's pretty clear from commercial products that 8-bit integer is enough. You don't need 32-bit float, which was the default that people were using beforehand. Within the research community, people have been pushing this to much more kind of extreme levels. So the very first thing that people have looked at is, can we reduce the number of bits to the level of a single bit per weight, so binary nets, which some of you may have heard of. And the idea of how to visualize this is basically looking at binary filters. So your filters are basically, as shown here, composed of 0 and 1 values. This was shown to work, but it has a substantial accuracy loss. So people tried to take a different approach, looking at more. The concept was reducing the number of unique weights that you might have in the neural net. Right, so rather than saying I'm going to reduce the bits, I'm going to reduce the number of unique weights. And if you've heard of some of the work like ternary weight nets or XNOR nets, that's basically falls into this category. So another way that these types of works are commonly framed is it's binary nets, but with some scaling to them. So this is the activations, but could you also do this in weights? We saw that the weight information is also quite substantial in the neural net. So actually, the concept of making the weight sparse, again, has already been examined several decades ago. So if we look at optimal brain damage, which was work by Jan LeCun back in 1989, he looked at whether or not you can remove certain weights in the neural nets based on how they affect the output, and then do some retraining, which basically means adjust the weights a little bit to reduce the error that comes from removing these weights that have minimal impact on the output. He showed that you can get substantial benefits in terms of reducing the number of parameters. So as you can see here, he can basically achieve more than half, 2x, 2.5 reduction in terms of number of weights while maintaining the same accuracy. So this is the optimal brain damage work back in 1989. Then more recently, this work has also been, this idea of removing weights has also been applied to the latest neural network. So back in 2015, it was shown that you could actually using this concept of pruning, remove the weights that have the lowest magnitude in the network and do some retraining and have substantial reduction in the number of non-zero weights in your neural net. Right, so this was demonstrated on AlexNet, and it showed significant weight reduction. So if you see convolutional layers, you reduce the number of weights by 2.7x, and even more impressively, in the fully connected layers, we're getting a 9.9x reduction in this work. Now, the challenge, of course, that we saw is that fully connected layers are becoming less, widely used, but nonetheless, this does give a 2.7x reduction in the convolutional layers. And then, as you can see, in terms of the overall reduction, you get about a 9x reduction in terms of the weights, and that's mostly driven by the reduction in the fully connected layers. And then you get a 3x reduction in terms of the multiplies and accumulates. Finally, one thing that people have also looked at is the network architecture design itself. So we kind of hinted towards this at the beginning of this webinar. And the idea is that can we basically, rather than using these large filters, can we represent these large filters with a set of smaller filters, because smaller filters tend to require fewer weights and then also fewer computations. So one thing that was looked at in terms of the Google network was looking at, let's say, can you decompose the 5x5 filter into 1x5 and 5x1 filters. So in fact, you're basically separating the filters based on their, you can think of it as their height and width dimensions, right? This is actually, this concept of separable filters has been around a while in, the image processing domain. So when I teach this image processing class, in the very first lecture, we talk about separable filters, right? So it's a widely used technique for image processing, and it's been kind of rediscovered for the neural nets. And the idea is that once you've separated your filter into the height and width domain, then you can apply them sequentially on the same input data. And the overall effect is that you achieve a 5x5 filtering. The drawback of this would be that the number of types of filters that you can represent, right? So the degrees of freedom has been reduced. So rather than being able to represent filters with 25 different weights, now you can only represent a set of filters with only 10 different types of weights. So this is, again, used in Inception v3. Another approach of decomposition that people have explored is in VGG, where they're looking at you basically decomposing the 5x5 and 7x7 filters in VGG down to only 3x3 filters, or 2 3x3 filters. And then again, applying it sequentially. So the nice thing about the VGG work, if you've looked at it in the past, is that all the filters are all 3x3. But again, the number of channels, the number of filters will still vary. Another popular approach from a network architecture point of view is to use what they call a 1x1 bottleneck. And the idea is that you have these 1x1 filters that really compress and reduce the number of channels that are generated for the next layer, right? So what you want to do is that, as you call, the number of filters dictates the number of channels of the next layer. So if the number of filters you have is less than the number of channels in the current layer, then the number of channels in the next layer will be reduced. And so this is widely used. So ResNet uses this in their design. So this is the shortcut module that ResNet uses, which I won't get into. But rather than having 2 3x3 filters, they insert a 1x1 bottleneck beforehand to compress the dimension down before they apply the 3x3 filter. And then they do a 1x1 to expand it back out to the same number of channels so that they can combine it with the skip module. GoogleNet, you also see this. So they typically use this 1x1 convolution to compress before, again, the larger filters. So you can see before 3x3 and before 5x5. GoogleNet uses this 1x1 bottleneck. A piece of work that actually does this to kind of the extreme is SqueezeNet. You might have all heard of SqueezeNet. They have this Fire module that uses a lot of these 1x1 convolutions. And SqueezeNet was very successful in terms of significantly using these bottlenecks to significantly reduce the number of weights that there are in the neural network itself. Right? So SqueezeNet is able to reduce the number of weights by 50x compared to AlexNet, but still have the same degree of accuracy. All right, so in terms of, we've talked about, accuracy. If I were to give you a neural network in terms of accuracy, it's pretty easy to measure. You can measure it on a given data set. You can very roughly speaking maybe estimate the speed given the number of max in the neural network. In terms of the storage footprint, you can see that from the number of weights. But one thing we haven't directly addressed is if I were to give you a neural network, could you tell me how much energy it would actually consume? Just looking at the specs in terms of number of ops, number of weights, and so on. So that's actually a non-trivial thing to do. So one of the tools that has been developed is this energy evaluation methodology. This comes from my group. And so the idea is that what you can do is you can put in the different shapes and configurations of the CNN into this energy estimation tool. And you can also give it the weights and the input data in terms of showing its sparsity. And what it will do with this tool is that it will look at not just the number of MACs, but also how you might allocate the different layers of the network, the different shapes and weights at the different levels of the memory hierarchy. So you can have a breakdown in terms of the energy access and the data movement that occurs at the different levels of the memory hierarchy. Because as we recall, data movement really dominates the energy consumption. And so at the output, what you'll get is an energy breakdown in terms of the amount of energy that's consumed per layer and also where it's being consumed in the network itself. And so using this tool, we really want to take this and kind of analyze the energy consumption of all the different neural networks that we've seen before. And so one thing that really observed is that the weights alone actually are not a good metric for energy consumption, right? So if you look at GoogleNet here, we can see that the weight energy is only around 22% of the energy. So you shouldn't really, look at a network, say that it has very few weights, and assume that it's going to be very energy efficient. That's not necessarily going to be the truth. So if we use this energy model to profile the different CNNs that we talked about so far, we can see already the automatic trend here. So shown here below is the energy consumption of the horizontal axis, and the vertical axis is the accuracy. So basically, as we move to the upper hand and to the top left-hand corner, the better we are. So what we can see is, first of all, the deeper CNNs with fewer weights don't necessarily consume less energy than shallower CNNs. So for example, GoogleNet and SqueezeNet both have less weights than AlexNet, but they still both consume more energy than AlexNet itself. When we're looking at ways to remove or reduce the energy consumption, one approach that we saw was removing the weights with small magnitudes. And you can see that by doing this, shown here in the green, it maintains the same accuracy, but the energy consumption is actually reduced. What we suggest doing is also kind of factoring in the energy consumption as well when you're doing the weight removal. So for example, what you could do is that you could sort the networks or sort the layers based on the highest to lowest energy, and then start removing weights from the highest energy layers first, because as you remove more and more weights, it's going to be more and more difficult to do so. So you really want to attack the layers where there's the most energy. And here we show that you can get about a 3.7x reduction in AlexNet and a 1.6x reduction in GoogleNet. And compared to not, factoring in the energy, you get about a 1.6x reduction compared to the 1.7x reduction compared to the previous work. I don't have too much time to talk about, but some of the other things we will be exploring are more kind of structured pruning. So here, this is looking at, pruning weight by weight. And so you might need to have specialized hardware to support this type of pruning. You could also prune kind of groups of weights, and that would be more amenable to SIMD type of architectures. So to summarize, we looked at various different energy efficient approaches. Primarily, if you care about energy, you're trying to focus on minimizing data movement. At the same time, you really need to balance flexibility and energy consumption. And you want to really exploit sparsity. Sparsity is something that's really kind of coming into play in terms of the space, both in the weights as well as in terms of the feature activation. We saw that joint algorithm and hardware design can be a very nice way of addressing all the different metrics that we saw. And what we're hoping is that currently, you get for a linear increase in accuracy, you require an exponential increase in energy, eventually throughput as well. And so what we're hoping is that with this joint algorithm hardware design, we can actually help improve this trade-off. This is just a very brief summary of a wide scope of work. There's obviously a lot of work in DNNs out there looking at making it more efficient. So I just wanted to point you to a couple of references. We have an overview paper that would cover it. We also have some slides from a full day tutorial that we do on this. You can also visit that. And we'll be running a course out in Silicon Valley early next year. So if you're interested in that, I would suggest checking that out. So now I'll turn it over to Brian.
Thanks, Professor C. I'd like to say just a few words about the Embedded Vision Alliance. The Alliance is a partnership of approximately 70 technology suppliers, and our mission is to help developers like those of you on this webinar to build better products by incorporating visual intelligence in them. You can find additional extensive resources focused on practical computer vision technology at the Alliance's website, which is www.embedded-vision.com, where you can also sign up for our newsletter. The Alliance also organizes Embedded Vision Summit events. The next one will take place May 22nd through 24th, 2018 in Santa Clara, California. The summit is the event for innovators who want to bring visual intelligence to their products. It includes multiple days and 3 tracks worth of presentations, along with keynotes from well-known and influential industry members. At the Technology Showcase, top suppliers demonstrate the latest developments in computer vision technology, and both partial and full-day workshops provide opportunities for even more in-depth education. Please check out the videos and other materials from the May 2017 Embedded Vision Summit, now published on the Alliance website, and reserve May 22nd through 24th, 2018 in your calendar. More information on next year's summit, including online registration, will be available soon on the Alliance website. At the conclusion of this webinar, you'll be invited to complete a very short survey detailing your thoughts about today's event. And I strongly encourage you to fill it out so that we can learn how to make future webinars even better. A common question that was asked to me today privately, tomorrow at the same time, you'll receive an email from us explaining how to access a PDF copy of the slide deck, the archived video of the webinar, and additional information on deep learning for embedded vision and other computer vision topics. Please keep an eye out for that in your inbox. Thanks again for attending today's webinar, Efficient Programming for Deep Learning, Challenges and Opportunities, presented by Dr. Vivian C., Associate Professor in the Electrical Engineering and Computer Science Department at MIT, and organized by the Embedded Vision Alliance. Have a good day, everybody.